Swayam Prabha. Digital India. Educated India.
So proof, well, the proof is again simple. It is basically exactly what I have said so far. I will not write down the proof. Let me just give the sketch. You can complete it. So it follows by induction. Okay. So what is our induction hypothesis? So we maintain the so the induction is on the depth of the circuit, and the hypothesis that we maintain is that at node V at, well, is it called depth or, well, depth probably, yeah, at depth D, CV of x is 0 and CV of y is 1. Okay. So if V is the root node, then this is true by the assumption itself that C of x is not equal to C of y, because f of x is equal to 0 and f of y is equal to 1. So at V, if V is the root, then this is true by well, the definition that we have. Now suppose it is true at any node V, okay, if the induction hypothesis is true at V, show that it is true at either VL or VR. Okay. Now, how many bits are communicated? So I'll just leave this. So how many bits are communicated in this protocol? So the number of bits, so let's give a name to this protocol. So let's call this protocol as pi. So we have that the number of bits communicated in this protocol is at most the depth. Okay, whatever is the depth. Any questions? So again, the idea is actually very simple. So well, Alice and Bob, they kind of just try to find out which side they need to go to in order to maintain this invariant at every node of the path. That's all. And they can actually do this because because when you are at a current node, you already have this property. So therefore, it must be true at one of the two children.
What is that? Is the
CV of x. Okay. So CV of x is, so C is a circuit. X is an input to that circuit. And suppose V is a node in that circuit, right? So
on that input, if we provide this x input to the
circuit, on that node V, what is it outputting? Yeah.
Sir, but the, I mean the total, I mean the power is the input length for the circuit C? If it is n, then is the length
input length for the circuit. So Alice and Bob have okay. So one more thing is that Alice and Bob have unlimited computational power. So both Alice and Bob have a copy of the circuit with themselves. They know what the circuit is.
saying that suppose there is the circuit C and the input length for the circuit is n. It takes
Right,
inputs of length
right,
n.
right.
So and the x that Alice has,
Yes.
I mean, is that x is of length n?
Yes. It is an input which evaluates to 0 on that circuit by definition. And y is an input of length n again, which evaluates to 1 on that circuit. Okay.
But in the example that we considered, we divided that.
Where? No, we are not dividing. So in the process, so again, if you look at that XOR thing, okay, so we are looking at an input on which the function XOR evaluates to 0, another input on which the function XOR evaluates to 1. Then during the protocol, we are dividing that input in a appropriate manner. Yes.
If it's a root, let's say it was AND, and then L, let's say it was a OR, then accordingly as we described, let's say if it was AND, then we saw that Alice would have to take the call on whether to go on left or right. But if it's a OR, then Bob has to take a call on whether it has to go left or right. So then if it's an AND and at the next level it's a OR, then the first level, root level, Alice will take the decision, and at the second level, Bob will take the decision.
Yeah.
Just depends on like what the gate is.
Yes.
But the communication complexity problem, the goal is to find out the difference in bits.
Well, the way we defined, so we have defined this problem R of f, where we want to find out an index on which the two, I mean, on which x and y differ. So here, yes. So see, the communication complexity problem in general is what I said earlier. Okay, so you can think of it as we want to compute a function f which depends on two inputs, x and y. Now Alice has one part of the input, Bob has another part of the input, and they want to compute f of xy. Right, so f of xy is the index I on which x and y differ. So we are defining f in that particular manner. Okay. Okay. So now let's look at the other direction. Other direction is also simple. So now we are given a here we have designed a protocol. So now given a protocol, we will design a circuit. So we will prove that B of f is less than or equal to C R of f. Okay. In fact, what we will show is something well, slightly stronger probably. So it suffices to prove the following. So we'll prove the lemma that if A and B are subsets of 0, 1 to the power n such that A and B do not intersect. Okay. And the communication complexity of R AB is at most D, then there exists a function f Boolean function such that on entire A it goes to 0, on entire B the function goes to 1, and there is a circuit for this function of depth at most t. So what are we saying here? So take two sets. So here we are talking in terms of sets. So we have two sets which are disjoint, okay, some two subsets, and the communication complexity of this relation is at most t. Okay, so if Bob is given x belonging to A and Alice, if Alice is given an x belonging to A, Bob is given a y belonging to B, they can compute an index on which x and y differ in at most d bits. Now what this is saying is that there exists a function f such that f of A goes to 0, f of B goes to 1, and d of f is at most d. Okay. There is a circuit for f which has at most d depth. So how does this, okay, so let's just spend a moment and understand that how does this lemma give us this inequality. Okay. So first of all, if C of Rf is less than D implies D of f is less than D, then we get this identity, right? If C of Rf is smaller than a quantity D gives us that D of f is smaller than D, then it must be the case that D of f is less than CR of f, right? But how does this give us that C of Rf is less than D? How do we get? What does it mean to say that C of Rf is less than D? C of Rf is less than D if f inverse 0, if A were to be f inverse 0 and B were to be f inverse 1. But why is that true? Well, okay, let me put it slightly differently. So what I can do is, so let's say I am given a function f, I want to compute CR of f, right? I want to find out what CR of f is. I can choose A to be f inverse 0, I can choose B to be f inverse 1. Then of course I get the hypothesis of this lemma that A intersection B is empty, and I get that, well, RAB is equal to, by definition, R of f. Okay, that is the definition of that. Okay, but then what this says is that there exists an f on which this happens. So that f need not be the same f that I started off with. It can be some other f prime now, right? So this is only saying that there exists an f on which this is true, D of f is true, but this can be some other f prime. What I need is that for the f that I started off here, I should have D of f less than D. But this can be some g, okay. So
what does it mean? What is the nature of this function which is acting on these sets? Like according to the notation.
which function? Oh, this one, yeah. This means that f of x is 0 for all x in A. Yeah. Yeah, so f of a set equal to 0 means for all inputs of that set it is mapped to 0, and the same thing here. So do you get the problem here? Okay, so again, so let me just to understand this in a better way. So instead of f here, just let me rewrite this as g. Okay, that I think will make it more clear, because f is a little bit we are using f in a different context. So there exists g such that this and d of g is at most d. Okay, so suppose if I start with a function f, okay, and I want to find out, I want to show that C of Rf is bounded or D of f is upper bounded by C of Rf. Now if I want to apply this lemma, what I do is that I set A to be f inverse 0, I set B to be f inverse 1, I get the hypothesis that A intersection B is empty, and I get that, well, R of AB is the same as R of f. So therefore CRF is at most D. But now what this is saying, that there exists a G on which this happens. Therefore, I get d of g is at most d, but what I actually need is d of f should be at most d. Exactly. So, if there exists this g, then it must be the case that g is equal to f, because by my definition, if, sorry, this should be g again, yeah, g of a, g of b. So, if by this thing, if there exists a g such that g of a is 0 and g of b is 0, it is actually matching with f. F of a is, we know that f of a is 0 and f of b is 0, and g of a is 0 and g of b is 0 implies that f is equal to g. So, therefore, what we get is that d of f is also bounded by d. Okay. So, therefore, proving this lemma would prove the result for us. Okay. So, now let us look at the proof of this lemma, and that would complete the theorem. So, the proof is by induction on D. So, we start with D equal to 0. So, if D is equal to 0, what does it say? So, if D is equal to 0, then what we have is that C R A B equals 0, which means that Alice and Bob can compute the relation RAB without communicating any bit. What does that mean? What does that say about A and B? Huh? They cannot be the same, so they are disjoint, so they cannot be same. Exactly. So there exists an index I such that for every pair x comma y, x and y must differ on that particular index. So Alice and Bob, without actually communicating anything, they would just say I is the index. Okay. So there exists I such that for all x y belonging to A cross B, xi and yi differ. So which means that no matter what x Alice has and what y Bob has, they would just output I. They don't need to communicate anything. Now suppose the lemma is true for D minus 1. Okay. Now we have to prove it for D. So what do we have? Correct. We have to specify what G looks like, right? So we have to say what is the function G such that this happens. What would be the function G? So if there exists an I, then what would be the corresponding G?
Xi or Xi bar, this will depend on.
Okay. So then G is either Xi or not of Xi. Okay. Such that G of A becomes 0 and G of B becomes 1. Okay. Whatever it is, I mean, if the elements in A have it as Xi, then well, it will be Xi, and if the elements in A have it as a not of Xi, then it will be again not of Xi, whatever it is. Okay. Now suppose the lemma is true for d minus 1. That is, if CRAB is at most d minus 1, then there exists a G such that d of G is at most d minus 1. Okay. Then what can we say about D? Let pi be the protocol for RAB, okay, whatever is that protocol, let pi. And without loss of generality, suppose that Alice sends the first bit in this protocol. So either of the parties can send. Suppose it is Alice who is sending the first bit. Now, what happens to the, so if Alice is sending, so Alice, note that Alice has an element from A. So if Alice is sending a bit, what does that do to A? So what can be Alice's bit? So Alice's bit can either be 0 or 1. Okay. Now what does that 0, 1 do to the set A? So what it does is, it is partitioning that set into two parts. Okay, it is partitioning that set into an A0 and at A1, such that if that X was from A0, Alice would have sent a 0, and if that X was from A1, then Alice would have sent a 1. Okay. So this gives a partition of A as A equal to A1 union A2, A1 intersect A2 is empty, and if X belongs to, sorry, let me not write A1 and A2, let me write A0 and A1, A0 and A1, such that if X belongs to A0, Alice sends 0, and if X belongs to A1, Alice sends a 1. Okay. Now what do we have? So now we have actually broken down this relation into two sub-relation. Okay. So now we have, as a result, we get the following two relations R A1B and R A2B, right? So, and again, yeah, so R A1B and R A2B. And now if we consider the communication complexity of these two relations, CR A1B and CR A2B, what can we say? Well, now what we know is that, well, because already one bit is communicated, the communication complexity of these two relations is at most d minus 1. What else can we say? Well, we have to make sure that the hypothesis is satisfied. So this part is satisfied. A and B are of, so A1 and A2 and B are of course subsets of 0, 1 to the power n, that is clear. We also have that A1 intersect B is empty and A2 intersect B is empty, because A1 and A2 are subsets of A. So therefore, what do we get? So because it is for D minus 1, by induction hypothesis, what we have is there exist G1 and G2 such that, let's look at G1 first. G1 of A1 is equal to 0, G1 of B is equal to 1, and D of G1 is at most D minus 1. Similarly, G2 of I'm sorry, again I think I've confused it. So it is A0, A1, so it should be A0, A1 here, A0, A1, A0, A1, A0, A1, okay, and let me write this also as G0 and G1. So G0 of A0 is 0, G0 of B is 1, and G0 of D of G0 is at most D minus 1. Similarly, G1 of A1 is 0, G1 of B is 1, and D of G1 is at most D minus 1. Okay. Now, how do we get, what we have to show is that the claim is true for D now. So, using this G1 and G2, how can I build a G for such that D of G is at most D? How do I define G now? Y and
A is going to be like any element of A is going to be 0 either for G0 or for G1, and any element of B is going to be 1 for both of them.
right. Exactly. So, we define G to be AND of G0 and G1, because now any element, so now if I look at G of A, so any element in A must belong to either A0 or A1. So therefore, by this, if I look at the AND of both these zeros, so therefore on any element of A, G also must evaluate to 0 now, and because B is anyway the same, B is not changing, so therefore it is clearly true over there. And now what is the depth of G? So then what we have is G of A is now equal to 0 and G of B is equal to 1. So G of B is equal to 1 because already G0B and G1 of B were equal to 1, and the depth of this function G was whatever was the depth of G0 and G1, which was at most D minus 1 plus one more level. So it is at most D. Okay. Now this entire thing was when Alice had sent the first bit. Okay. What if Bob had sent the first bit? Okay. So if Bob sends the first bit, then so if Bob sends the first bit. What do we do? How? What? I mean, what exactly? Yes, it is symmetric, but what exactly do you need to do? So now instead of A, B is actually getting split because Bob is it is Bob who is taking the decision. So B gets split. So we have a partition of B into B0, B1. So everything is the same here. So now if X belongs to B0, Bob sends a 0, else Bob sends a 1. And finally, the function G that you compute will be G0 or G1. Okay, so if Bob sends the first bit, then B gets partitioned and finally G will be equal to G0 or G1. Okay, and that completes the proof of the lemma. Okay, so this also completes a proof of Karchmer-Wigderson's theorem, which shows us a tight bound, so which gives a tight bound on the depth of a bounded Fanon circuit over and or not, computing a function in terms of the corresponding communication problem, in terms of the communication complexity of the corresponding communication problem. Okay. So we will see some applications and some more stuff about communication complexity in the next lecture. So that's it for today.